All right, everybody. Today we're going to talk about the technique of calculating arc length, and it's actually pretty straightforward, although sometimes the integration itself can be a little bit sticky. Excuse me. The concept is pretty straightforward. So over here I have a couple of points in the xy plane, A and B, and I don't want to talk about the distance between A and B. That's just the distance formula. That's straightforward. What I want to talk about is the distance between A and B along a certain path. Right? So traveling from A to B along a certain path. Not how far. Not how far between A and B, points A and B, but the length of the path along A and B. And if I can even get you guys excited about this, I would say that this is the beginnings of your parametric journey for those of you that want to put things into orbit, travel to Mars. It's not a straight shot to Mars, and you begin by plotting a course and then calculating the distance along that path, not just the linear distance between Earth and Mars, right? So while this may be pretty mundane, it is your first step into a larger world when you get to Calc 3 and you can really start doing some damage with orbital mechanics, man. So anyhow, that's the idea. But how are we going to calculate this, right? So how do we calculate this? That's two words, by the way. Calculate this, question mark. Well, the answer might not surprise you. If this was Calc 1 and we were calculating area under a curve, I just draw a little bit of a function here. That's f of x. You begin to calculate that area, or at least approximate it, by cutting it up, as we saw in section 7.7, into approximating bits. Maybe you use trapezoids, maybe you used parabolas, left-hand rule, right-hand rule, midpoint rule, but we begin by cutting into small approximating bits. And we're going to do the same thing here. If I want to, for the length of the, let's call this f of x. If this is f of x, or let's say y equals f of x, and I want to calculate the length of curve between A and B, this length here, and I want to know how long that path is, what we're going to do is, in a very similar fashion to finding area, we're going to begin by cutting this up into subdivisions. We're going to subdivide the interval A to B, just like we would if we were using the trapezoid rule or Simpson's rule or any of those other rules. However, it's not even going to be near as crazy as Simpson's rule. So we cut this up, and what we have here is some small change in width that we're calling delta x. Now, for each one of these delta x subdivisions, what we're going to do is we're going to approximate, like the trapezoid rule, by drawing some linear connectors to the endpoints of each one of these subdivisions up on the function. And what I'd like to do is, I'd like to focus on one of these specifically. So let's see here. This would be x naught, x1, dot, dot, dot. Somewhere in between here would be an x sub I minus 1, an x sub I, and then at the end, x sub n. And I want to focus on this particular bit right here. Now, I'm not actually finding the area, so let's get away from that. But I have, in fact, let's call this 0.0, 0.1, 0.2, dot, 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 point sub I minus 1, point sub I, and point sub n. These are the points on the curve at either end of the subdivision. And really what we're doing is we're just using the distance formula a bunch. So let's see here. If I draw this, draw this a little bit bigger here. So let's say that this is p sub I, and this is p sub I minus 1. Well, that corresponds on the x-axis to the following subinterval, right? We know that this is length delta x horizontally. Let me draw that in here. And vertically speaking, this distance here we can call the change in y, roughly, between, or not roughly, exactly between those 2 points. And sometimes this horizontal distance is called delta s, or the change in arc. So this is delta s is the change along the path. Delta x is the horizontal change on the subinterval, and delta y is the vertical change. Now, the length of the purple curve here, or the purple line segment, this guy right here, which, I mean, classically speaking, I guess we could write that as, so this is some old school geometry notation, pi minus 1 to pi line segment. Or the length of that segment is the magnitude of that segment, or the absolute value, or its length, is delta s. Don't worry too much about this notation if it's freaking you out. I just want to find the length of delta s. And according to this little diagram, since this is a right triangle, it looks like delta x squared plus delta y squared is equal to delta s squared by Pythagorean theorem. And if that's the case, then what we're looking for here, delta s, is the square root of the change in the x direction squared plus the change in the y direction squared. I mean, this is a distance formula, right? So there you have it. Now, what we have here is, so let's call this arc length L. So L is the letter we're going to reserve for arc length. And L is approximately the sum from I equals 1 to n of all of these little line segments lengths. Or if you like, it is the sum from I equals 1 to n of each one of those little delta s's. So let's call this delta s sub I, delta y sub I in the ith interval. And we could call this delta x sub I, but delta x is going to be the same for each one of these intervals up here. However, the change in y is going to be different from interval to interval. Sometimes it's negative, sometimes it's positive. And as a result, that little delta s is going to be different in each interval as well. And that's what's going to give us our different arc lengths for different curves. Anyway, all we're doing is we're adding up all of these little bits along this curve. Delta s sub 1, delta s sub 2, delta s sub 3, 4, 5, general ith, and nth one at the end. So that's our little generic formula for it. It doesn't say too much. All it says is add up all the diagonal bits of length. Okay. But we have a formula. Let me put some sub i's on this here. So that then becomes the sum from I equals 1 to n of the square root of delta x. I would put sub I there, but all the delta x's are the same. Plus delta y sub I there squared. Now, that is what the arc length is approximately. So how can we get a better approximation? Well, just like in any calculus scenario, if you have a curve and you want a better approximation, instead of using giant arc lengths to calculate that length, giant line segments, we're just going to cut this up into bits. That is to say, if I want the length between x equals a and x equals b, I will get a better approximation if I use lots of really small line segments. And the smaller they are, the better, until the actual arc length is, so let me stress this. This was an approximation. But now I have actual equality if I take the limit as the number of little segments tends towards infinity of the sum from I equals 1 to n of the square root of delta x squared plus the delta y sub i's squared. And that is almost the definition of definite integral. I got to do a little bit of manipulation here. So aside, in order to turn that into an integral, I really need to have a delta x on the outside, and I don't have that. So what I'm going to do here is I'm going to take delta x squared plus delta y squared, and I'm going to factor it. And you might say to yourself, how are you going to factor that, Jenkins? There's nothing to factor out. Psh, dude, watch me. Nailed it. I didn't say it was going to go in pretty, but there it is. I factored out a delta x squared. That's going to allow me to rewrite this as delta x squared under the square root times the square root of 1 plus, and I'll rewrite this as the quantity delta y over delta x squared. So this then becomes equal to the limit as n approaches infinity of the sum from I equals 1 to n. I'm going to write this term first. The square root of 1 plus the quantity delta y sub I over delta x sub I squared. And then the square root of delta x squared is just delta x. So check. Now we have what we're looking for. And that's going to allow me to rewrite this as the integral from a to b of the square root of... Now, in the limit as n goes to infinity, we don't write this as delta x anymore. It becomes a dx, which means that underneath the radical here, we're going to get 1 plus dy over dx squared. And I'm going to rewrite this one more time. L is equal to the integral from a to b of the square root of 1 plus dy over dx squared dx, but dy over dx, another way of writing that is the derivative of f prime of x, since f of x equals y. So this is our formula, and you can if you look at it, stare at it long enough, you can see the distance formula hiding in there. You got to squint a little bit, but it's in there. And this is our formula for calculating arc length. Now, alternately, we could have just as easily flipped this around and done this sort of as a type 2 curve, which wasn't a function, and integrated it with respect to y and done our little arc lengths, maybe vertically if we wanted to, and the alternate version there would have been the integral from c to d of the square root of 1 plus, it would have been dx over dy, but that's just f prime of y dy. So for with respect to y. So you can do it that way if you want to. If you have a weird curve that is not a function. This is for non-functions.